Well, this is the first of a handful of lectures about Chapter 4, which has to do with queuing theory and applications, as the title says. Now, this course is cross-listed as an undergraduate course at IEE 421, yes, 421, and IEE 521. And if you are an undergraduate engineering industrial engineering major, you may have had this information already in a course that is IEE 470, which I think is called Stochastic Operations Research. If you're an engineering management major undergraduate or informatics undergraduate or any other major but IE, you may not have had this course. If you're an IE, you might not even have had this course just yet. And that, I just want to assure you, is perfectly okay. Now, some of you have had this course, and some of you may be taking this course now. And so, for those of you who have had this course or are taking it now, you may find what I'm about to cover to be review, okay? Or at least in parallel with something you're learning right now. If you're a graduate student, I have no idea where you take queuing theory or if you've had it before. Anyways, this long introduction is really the purpose of it is to let you know that I am going to cover queuing theory applications as if none of you have ever seen it before, okay? Just so we all have, we're all playing on the same field, basically, okay? So just wanted to let you know that. Okay, now we're not going to cover the whole chapter, so I've combined some of the sections, and then when we get towards the end, you're going to see that I basically say, well, we're going to ignore the rest of it. So right now we're just going to introduce you to some background, some terms, and some notation that the textbook uses. And I'm going to try to let you know about some other notation that is sometimes used when you take queuing classes or when you read about queuing applications in textbooks. So here is our just very general queuing system. We are going to have users or customers, if you will, come into the queue. It'll be a single queue, and then they will go to the first available server. So the number of servers in a queuing system, according to the textbook notation, is going to be M. Sometimes you see, and I just want to point this out, because in other books, sometimes M is S in other textbooks. Just letting you know. What else here? And we're going to be, yes, so they're going to go to the first available server. This always reminds me a bit, if you've ever been to Fry's Electronics on Baseline Road, they have a single queue and then they have a whole bunch of servers here. Once the service is complete, then they're going to depart from the system. So that is our general or generic queuing system. Let me put this over here. We're also going to be referring to the queuing system as being in a certain state. And the text, it's really dependent upon time, but this textbook uses N to represent the number of people in a system. So we could be in state 1, 2, 3, and for some reason I forgot 0. We could be in state 0 where we have nobody in the system. So a system state is referred to, as I said, as these integers. Sometimes it can be finite if the queue is finite, but we're always going to add the number of people who are in service plus the number of people who are in the queue, or queue, I probably should have said is a waiting line, number in queue, the people waiting for service. So for example, if I had 2 servers, and we're always going to assume that our servers are identical. So suppose I had 2 servers here. I'll just say server 1 and server 2. And if we have nobody at any of the servers, then we would say we're in state 0, so nobody's there. If we have a person in service, and they could be either here or here, we will say that we're in state 1. If we have, you get the idea here, right? This is state 2. State 3 is 2 in service and 1 in queue. State 4 is 2 in service and 2 in queue, and so on. So So right here, this is showing right now, this is what we would call state, and I'll just put it in quotes, 4, because there's a total number of people in the system. In state 0, let me write it this way, state 0, all of the servers, and we can also have a single server as well, all servers are, and that's IDLE, idle. That means that they are not working. So that's a term that you will see. Here's the notation that the textbook uses, and again, I'm going to probably show you some alternative notation just because I think that's sometimes helpful. So again, a queue is a waiting line. We're going to have the system states as being, they could be finite or they can go on forever. M is going to be the number of servers. As I said, sometimes we see that as S, sometimes. And then P sub n, that's going to be the steady state. That means that, you know, when you start up a system, until it reaches steady state or where there's not a lot of variation, we refer to our queues as being in steady state. So imagine like when the doors of a Target open, it's not in steady state for, I don't know how long, 20 minutes or 30 minutes, because people shop and then they get into the cashier's line, and then it starts to get to steady state. Anyways, sometimes you see these referred to as the pi n or pi j. So I'm going to go up here too. Often we see the states of a system. I'm going to write this. I just want to show you the other notation that you might have seen. J sometimes in other texts, and pi sub n or pi sub j. Again, I'll put these in quotes. Sometimes. That's how I learned it. I'm showing you how I learned it. I learned using J's, S's, and pi sub J's. This is pretty much the same universally. We're going to have lambda is going to be my arrival rate. We're also going to refer to that as a birth rate, and we will have the service rate as well. Now, this is sometimes state dependent, but often it is not. So if it's not state dependent, we're just going to refer to this as lambda. That would be not dependent upon the state. And most of our applications use just lambda and mu, but I think there's a couple of examples that I will end up doing where lambda and mu are state dependent. So again, not dependent upon state. So let me give you an idea about what I mean by dependent upon state or not dependent upon state. Suppose it's a Friday night, it's like 6:30, you're driving around, you want to go out to dinner somewhere, you know, when we used to be able to go out to dinner, and you see a line at your favorite steakhouse. So you can see that there's people waiting outside. So that means you say, okay, I don't really feel like waiting that long, so I'm not going to go to that steakhouse. So the arrival rate to that steakhouse may have been different when that line was non-existent versus now that there is a line, because the line is influencing the rate at which people are showing up. Same thing with service rate. Sometimes the service rate is state dependent, and it actually is really state dependent if you have multiple servers. Actually, you're going to see this quite a bit in the next couple lectures. But if I have 3 servers and they're all busy, they're working at a faster rate in general, number of services per whatever time unit, versus 1 server who is busy and the other 2 are idle. So I kind of want to give you an idea of what we mean by state-dependent service and arrival. And the notation that we'll be using here, and my arrows are off, your slides are better than mine, I printed them and then I fixed them up a little bit. We're going to be seeing these letters quite a bit, M, G, D, and E. There's even some other ones eventually, but when we talk about, we're going to be talking about things like M, M, S, Q, or M, M, 2, Q. See, I just reverted back to my old notation. So the first indicator here is almost always M, meaning that we have a Poisson process, meaning that my arrivals are according to a Poisson process and my inter-arrival times are exponential. So inter-arrival times, Poisson process, exponential, inter-arrival times, exponential, inter-arrival times. And often, the second indicator here is also M, meaning that I have a Poisson process as well, and my service rate is going to be according to a Poisson rate, and that my service times are going to be exponentially distributed as well. And then that third one is the number of servers in my system. So it can be as small as 1, it can go up as much as you want. Sometimes we have distributions that are Erlang with parameter K. Sometimes we also teach it as Erlang with parameter R. Degenerate means that we have a constant service or a constant arrival rate. And general just means it could be anything at all. So here's some examples of the ones that we'll be doing in this course, and actually one that we won't be doing. I'm going to be doing just M in this course. So that's what that'll look like. So an MM1 means we have exponential enter-arrival times, exponential service times, and a single server. So that's what this one is here. If I'm talking in general, little m, then we have multiple servers, so we have 2 or more here. This was an MG1, so we have general service times but exponential enter-arrival times. And then here's another one, MDM, and you could have an M and then an Erlang K or whatever. But in general, we're going to be working. Actually, we're only going to be doing these in this course. So I'm going to write this down: 421, 521 only. Okay. Now, when we're doing queuing analysis, we're interested in certain types of quantities. We're interested in how long we're in the system, how long we're in the queue, what the length of the queue is, what the total number of people are, and we're often interested in the average values of those. So I'm going to talk about the quantities of interest and then these relationships between these quantities of interest. One of the things that students often get a little bit stumped by, or tripped up by, I should say, is when a problem expresses, are they expressing mu or lambda, or are they expressing 1 over mu or 1 over lambda? So just as a reminder, if we're talking about lambda and mu, or for that matter, lambda and mu n, if it was state dependent, these are rates. So when we say we have a lambda of 2 customers per hour, or a mu of 6.5 customers per day, that is always something per unit time. 1 over lambda and 1 over mu, or for that matter, 1 over lambda n and 1 over mu n, would be just units of time. So if we're talking about lambda and you see the words, and this is in general, it's not an exhaustive list, but you are being told exactly what lambda is if the wording in the problem or situation is that the mean arrival rate is, or the arrival rate is, or the arrivals per unit time is. You are being given lambda directly. If you are being told that the expected inter-arrival time is, or the mean inter-arrival time is, you're being given 1 over lambda. We've had some experience with this, already. I'm going to try to see if I can focus this a little bit better. Give me a second here. That looks pretty good. Let me just, I'm going to make sure I've got this. Yeah, we're good. Okay. You are being told directly what the service rate is. If you're told mean service rate is, service per unit time is. You are being told the expected service time, or 1 over mu if it says expected service time, or mean service time. So I wanted to clarify that. Most of you already know that, but it is something that you have to get used to, and it's something that certainly tripped me up a bit when I was first learning some of these things. What are the quantities of interest that we want to take a look at? Well, we are, as I said, going to be interested in, well, what's the probability that we are in state 0, for example? What's the probability that nobody's in the system? That means that my servers are being underutilized. So we don't want P0 in some cases to be particularly large. So what's the steady state probability of being in that state? We are interested in, and these are conventions here, L. That's the expected number of customers in the system. LQ is going to be the expected number of customers in the queue, but it doesn't include the customers being served or who are in service at the moment. W is going to be the expected waiting time in the entire system, so it includes the time in the queue and your time in service. And WQ is the expected time that you'll be spending in the queue only. And for a constant rate lambda, we have these universal equations that always hold. So let's take a look at your basic fundamental queuing model, and that is based upon something that we call the birth and death process. So the birth process means that we have arrivals, so that's like a birth, right? So a happy arrival. And the death process is when we take care of that arrival with a service. So this is a general view, pretty darn general, of a birth and death process. So let's take a look at it here. So each one of these are system states. So for example, this would be state 0. This is state 2, meaning there's 2 people in the system, and we can go on, and sometimes this can actually be finite, so we might just be able to stop there, but sometimes we could have a theoretical number of states that is actually infinite. So for large T, that means once we're in steady state, we're going to have these flow balance equations for each one of these states, and they are going to be determined. I'll use a different color here just for fun. In general, that my expected rate into a state, or arrival rate, I'm just going to say my expected rate into a state, that has to equal my expected rate out of a state. That means we're in what we call steady state. So expected rate out of a state. And how are we going to do these balance equations? Well, my rate of departure, so into a state, that's what I mean by arrivals or births, if you will. And this is departures or deaths. So how do we get I kind of got it backwards here, my rate of departures from state N? That's going to be my expected rate of departure will be the rate of departure times the probability of being in that state. And that's just like a regular expected value, right? The expected value of a random variable x is the probability that x equals that value times the value. So it's no different here. Same thing for my expected rate of entrances, or my expected arrivals into a state. That is going to be the rate, now this is where it gets a little more complicated. It's going to be the rate of entrance into the state from state n-1 times the probability of being in n-1 in the first place, plus the rate of entrance into state n from being in the subsequent state times the probability of being in that state. And I'm going to be able to show this a lot better on my next example. So let's take a look at that. And notice here too that we've got here, we have state-dependent arrival rates and state-dependent service rates here. So service means we're going, so if we have one person in a queue, one person in service, then the rate at which we move from state one person to nobody in the system is a rate of mu1. If we have 2 people in the system, then we move to state 1 at a rate mu2, and we advance to state 3 at a rate lambda 2, meaning that's the rate that is dependent upon this state. So this is a birth and death process. So let me do an example here to show you what I mean by births and deaths and balance equations and all that good stuff. I love my PhD in industrial engineering is in a focus on operations research. I just love this stuff so much. So imagine that we have customers and they're arriving in a fast food drive-thru. I'm sure you're all aware of that. We're going to pretend it's like a very small fast food drive-thru, and this is a simple little example. And we've got Kyle. Kyle's the only employee working the window, and he's able to serve 15 customers per hour. But the excuse me, the customers are arriving at a rate of 10 per hour. Okay, so there's only room for 3 cars in the system. So imagine that we have, maybe it's Maybe it's a very, very small drive-through in some strip mall somewhere, and there's just not a whole lot of room. So let me kind of just draw a picture here of what we're talking about. So imagine that we've got our drive-through window here. So we've got server Kyle here. And it says we've only got room for 3 cars in the system. So I'm just trying to show a simple example of a birth and death process. So we would have, this is going to be car 1. So this is the car that's in service. And we have room for only 3 cars in the system. So right here, this would be an example of our system at full capacity. So right here, we see that this would be state 3. We could be in state 2. We could be in state 1. We could be in state 0. So we have 4 possible states for this simple little system. So what have they given us here so far? Well, I know that I only have 1 server, so I know that my number of servers is 1. I know that it says, because they didn't tell me that they were state dependent, so I know that my rate, 10 per hour, is my arrival rate is lambda equals, and I guess it's 10 cars per hour. And Kyle is able to, his rate of service is 15 cars per hour. And you know what? You can do this in minutes, and it all works out exactly the same. So I could have expressed lambda as being 1 car every 6 minutes. I could have expressed mu as being 1 car every 4 minutes if I wanted to, and it always works out. So let me draw the state. First I'm going to draw, this is what we call a state transition diagram. So let me draw that. Is this coming out? State transition diagram. So we only have 4 possible states here. We have state 0, where nobody is in the system. We have state 1, where Kyle is taking care of a car. We have state 2, where Kyle is taking care of a car and there was 1 waiting. And then finally we have state 3, where 1 is in service and 2 are in the queue. So this would represent the queue, Q-U-E-U-E, and that's the car in service. So now we're just going to draw my birth and death process here. So I will move from nobody in the system to 1 person in the system using at a rate of 10 cars per hour. So I'm just going to write lambda equals, I'll just write 10 per hour here because I'm running out of space. And then I go from 1 to 2 people in the system at that same rate. So all of my lambdas here on the top arcs of this state transition diagram are all going to be the rate of lambda of 10 per hour. 10 cars per hour. And then I'm going to be, my Kyle service rate is at a rate of 15 per hour. So he will go from 3 people in the system to 2 people in the system by taking care of this car here at a rate of mu equals 15 per hour. And similarly, he'll go down from 2 to 1 car by having a service here. So that will be mu equals 15 per hour, and then also down here 15 per hour, like that. All right, now the question here is determine the steady state probability. So what they want me to find here, I'm going to put it in orange. They want me to they want the probability of being in state 0, state 1, state 2, and state 3. And the way we're going to do that is by doing what we call these balance equations. So I'm going to write that down here. I'll do, I'm going to use a thinner pen for that one because, so we said that it has to be rate in, rate out. So here's my balance equations. Or you call them state balance equations if you'd like. And I like to use, you can go do rate out, rate in, or rate in, or rate out. I tend to like to do in versus out. So I'm just going to write that here just so you know my protocol. So the expected rate into a system equals the expected rate out, or into a state equals the expected rate out. And so I'm going to write this by each state. So here's state, so we'll have state 0. And now state 0. How do we get into state 0? Well, we can only get into state 0 if we're in state 1. So the expected rate at which I get into state 0 is the probability of being in state 1 times the rate that I transition into state 0. So this is going to be, again, the rate at which I transition into state 0 times the probability of transitioning at that rate, and that probability will be P1 here. And that has to equal my rate out of state 1. So how do I get out of state 1? Well, my rate out of state 1 is 10, and the probability of that 10 is my probability of being in state 0. So that's my first balance equation, and that's associated with state 0. Then I have a balance equation that is associated with state 1. So how do I get into state 1? Well, I get into state 1 two ways. I can be in state 0 and have an arrival, or I can be in state 2 and have a service. So how would that work? That means that I have a rate of 10 times the probability that I'm in state 0 plus a service rate of 15 times the probability that I'm in state 2. And that has to equal my rate out of state 1. So I can get out of state 1 by having a service and going into state 0, or I can go out of state 1 and have an arrival, which puts me into state 2. So we'll write that this way. So we can have 15 times the probability I'm in state 1 plus 10 times the probability I'm in state 1. That gets me that arrival, and we could just write this alternatively as 25, well, let me write it this way, 25 P1. Let's do it for state 2. So for state 2, I think you can see where we're going with this. I can get into state 2 by being in state 1 and having an arrival, so we'll have 10 P1, or we could be in state 3 and have a service. And the way I get out of state 2 is, again, this lambda plus mu, but now times the probability of being in state 2. So we'll have 25 P2 right there. And then my last state, state 3, the only way I can get into state 3 is by being in state 2 and having an arrival. And the only way I can get out of state 3, because we're going to assume that any cars that find the system full are just going to leave. And now we can get out of state 3 by having a service and by being in state 3. Now, what I want to do is notice I have 4 equations and I have 4 unknowns, P0, P1, P2, and P3. The problem is, one of these are not linearly independent, okay? So we're going to have one more equation, and then we're going to have to toss one out. So let me write this out. These equations here are not, so these equations are not linearly independent. So that means I can't solve for 4 equations and 4 unknowns. So to solve for these unknowns, so to obtain P0, P1, P2, P3, we are going to eliminate one of these and then add another one that is linearly independent of these. So to obtain these probabilities, which is what we've been asked for, we are going to eliminate exactly one, and it doesn't matter which one. I like to choose the more complicated ones. Eliminate one balance equation and add the following equation. What do we know about these probabilities? Just like any other probability, we know that if we sum up from n going from 0 to 3 of each one of those probabilities, that we have to have 1. So what I'm going to do, and how did I do it? Let me see here. Yeah. So what I've decided to do, and I'll show you it on the next page, is I have decided to solve these. Which one did I toss? I tossed state 2. So I choose to eliminate the balance equation for state 2. It doesn't matter, okay? So I'm going to toss this one, and then I add this equation to the mix. I add, and maybe I'll put it in black so you know that I'm going to be using it. Now I'm going to add this equation, P0 plus P1 plus P2 plus P3 has to equal 1. So which of these equations will I be using? I don't have any other good colored markers here, but I'm going to be using this one, this one, this one, and that one to solve. Now, I have a suggestion for you. What you want to do is, you can do it by hand, which is probably how you learned it in, I don't know, high school maybe, or if you have a TI 83 or 84, or certainly an 89 or an Inspire, whatever, a calculator that will do matrix solutions for you, the row, echelon, whatever, you can do this and it will solve for your probabilities super nicely. So I'm not going to demonstrate this here because you all have different calculators, but this is what I did in my calculator. So let me show you, let me go back here, hang on a second here. Actually, I don't even have the calculator that I used here, but these are the equations, remember, from the previous slide, and I said I'm going to use state 0, state 1, state 3, and this one here. So in my calculator, so in Dr. C's calculator, I created, I called it matrix A. And so I would just Google how to do this. It works really well, and I don't even use 2% of what I should on my calculator. But this is the way I put it into my calculator. So you're going to have 1, 2, 3, 4. You're going to have 4 rows. I should not be using this pen. Hang on. So I have 4 rows in my calculator in matrix A here. And then I'm going to have 5 columns. So I'm just going to, it doesn't show it this way in your calculator, but the first 4 are going to be associated with what's my coefficient on P0, P1, P2, P3, and then the last row, or column, excuse me, will basically be your right hand side. So if I look at my balance equation here for state 0, and I put everything on the right that has a P in it and everything that's a constant on the right hand side, what would my coefficients be in my matrix? Well, I'd have a minus 10 here, and then I would have a 15, and then zeros and a 0 here. For state 1, if I put everything together, I end up with, again, we have a 10 here, but then we would have this P1 is 25 brought to the other side would be a minus 25, and then we'd have a 15 here, and then a 0 and a 0. My third equation, which is going to correspond to state 3, is going to have 0 for P0, 0 for P1 as a coefficient, a 10 here, and then a minus 15 here, and then a 0. And then finally, my last equation is going to have all 1s on the left-hand side, and then also a 1 on the right-hand side. So this is my matrix that I put in the calculator. Then I used all of this information here. I hadn't done it for a while, so it's kind of fun to remember how to do it. And when you solve for these probabilities, this is what you'll get. And I will take it to 4 decimal places for each one of these. And so the probability of having nobody in the system is 0.4154. The probability of having 1 person in service, nobody in queue, will be 0.2769. The probability of having one car in service and one car in queue is 0.1846, and the probability of having a full capacity, so this was the full capacity probability here, is that was one person in service, 2 in queue, is going to be 1, 2, 3, 1. And that's the answer to the question on the previous page. So that is a simple example of what balance equations are and the notation and so on. Next, the next presentation I'm going to give you is going to be specific to different queuing systems, and then we're also going to take a look at the things of interest like WQ, WL, and LQ. So onward and upward.